Hello, everyone. Welcome to today's lesson. Today, we are going to talk about the second part of the structural design of flexible pavement. The last lecture has covered the left part of this pavement design system chart. In this lecture, we will look into the design traffic followed by structural design of flexible pavements. A road pavement must be wide enough and of suitable geometry to permit all vehicles to safely operate at an acceptable speed. In addition, it must be strong enough to cater for both the heaviest of these vehicles and the cumulative effects of the passage of all vehicles. A traffic loading comprises different axle group types and different axle group loads. Normally, a vehicle has at least 2 axle groups. This vehicle has 3 axle groups, and each of a different type, from the single axle to tandem axle to tri-axle. Here, for the design traffic, the traffic loading is defined by the number of heavy vehicle axle groups, HVAG, not the number of heavy vehicles. The dominant vehicles in the 12 vehicle classification system classes are shown in the left figure. So we need to account for this variation in configurations of heavy vehicles when we characterize the loads on the pavement. We need to estimate the design traffic in terms of HVAGs for rigid pavement design. And for flexible pavement design, the HVAGs need to be converted to ESA, the equivalent standard axles, or SARs, the standard axle reputations. For pavement design, we need to identify the following 6 heavy vehicle axle group types: the SASD, SADT, TASD, TATD, TRDT, and QADT. From these figures, we could also see the meaning of single axle, the tandem axle, and the tri-axle in heavy vehicles. All tires referred here are for conventional tires. The pavement design task is to select a suitable pavement configuration for the traffic portion of a carriageway. The traffic way may vary from a single lane catering for traffic traveling in both directions to 6 or more lanes for single direction traffic. For multiple lane carriageways, the same pavement configuration is usually adopted for all lanes. The left part is a stepwise sort of procedure that you would use to calculate the design traffic. We will go to details of each part of this flowchart in the next few slides. Firstly, we need to select a design period, maybe 20, 30, or 50 years. Then find the annual average daily traffic, the AADT. We also need to know the percentage of heavy vehicles in traffic stream, the lane distribution factor, and cumulative growth factor. Then we are able to calculate the number of axle groups per heavy vehicle, an HVAG, and calculate the cumulative HVAGs in terms of design traffic and DT. According to these calculations and traffic load distribution, we are able to calculate design and allowable traffic loading to make a comparison and draw the conclusion. When we design a structure, we firstly pick a design period because that influences the number of actual load repetitions the pavement will experience. For the design period, it is the time period for the pavement to function without major rehabilitation or reconstruction. The adopted design period is typically 20 to 40 years for flexible pavements and 30 to 40 years for rigid pavements. According to what type of pavement you want to construct, you could select the design period within this range. For new construction, it is a common practice to adopt the same pavement design for all lanes of the carriageway and to base the design on the traffic loading in most heavily trafficked lane. The most heavily trafficked lane is termed the design lane. For a two-lane, two-way road, in other words, one lane in each direction, the design lane is readily identified as that lane which is most heavily trafficked. For multiple lane single direction carriageways, the design lane is, in the vast majority cases, the left or outermost lane. The weight in motion system are available, which provide lane-specific heavy vehicle traffic loading data across a carriageway. If project-specific information is not available, then the below table provides guidance on the proportion of heavy vehicle traffic loading assigned to the design lane. The proportion assigned to a specific lane is termed the lane distribution factor, the LDF, for the lane. So according to the pavement location, either is rural or urban, the number of lanes in each direction, either 2 or 3 lanes, and position of the lane, the lane distribution factor will be selected from this table. This is a typical weight in motion system for measuring traffic loads. The WIM system records the actual weight and the gross vehicle weight as vehicles pass it. So it could provide the lane-specific heavy vehicle traffic loading data across a carriageway. The WIM data also provides the number of actual groups per heavy vehicle required to calculate the cumulative number of HVAG and the distribution of actual group types and loads required to calculate the design traffic for flexible and rigid pavements. The first requirement of a pavement design is that it be adequate for the cumulative traffic loading anticipated in the design lane over the design period. Estimation of this loading firstly requires the calculation of the cumulative number of heavy vehicle actual groups, HVAG, over the design period. The equation to derive the design traffic NDT in cumulative heavy vehicle actual groups traversing the design lane during the specific period is shown here. The AADT is the annual average daily traffic in the first year, and DF is the direction factor, which is the proportion of two-way AADT traveling in the direction of design lane. Direction factor of 0.5 means traffic is divided equally between both directions. The percentage of HV is the average percentage of heavy vehicles. The LDF is the lane distribution factor, which is the proportion of heavy vehicles in design lane. CGF is the cumulative growth factor, and NHVAG is the average number of actual groups per heavy vehicle. The design traffic NDT is applicable for both flexible and rigid pavement. The average number of actual groups per heavy vehicle NHVAG could be obtained from vehicle classification codes from the WIM data, or if the WIM data is not available, then the presumptive values could be used. As shown for one example here, the presumptive NHVAG could be found from table the D1. These are the statistics that are for a different heavy location of NSW. So we can refer to this table to find the corresponding HVAG value. Now let's look at one example here. The weight in motion data given in table H1 is available for us to calculate an HVAG. So firstly, we need to estimate the proportion of steer axles from single tier actuals. So from table H1, the total proportion of the actual group, that's 1. So the sum of the proportion of actuals which are single actual single tier SAST and tandem actual with single tiers TAST is 0.3799 plus 0.0216 equal to 0.4 as shown here. So to estimate the average number of actual groups per heavy vehicle, it is assumed that there's one SAST or one TAST per heavy vehicle. So therefore, on average, 100 HVAG of loading results from the passage of 40 heavy vehicles. So the average number of actual groups per heavy vehicle is 100 divided by 40 and equals to 2.5. This example requires us to estimate NDT from equation 14, where the design parameters are shown below. The design period, that's 20 years, and the average daily traffic AADT, that's 5,350. Direction factor of 0.5. Percentage of heavy vehicle is 4%. The lane distribution factor is 1. And heavy vehicle growth rate is 12%. And NHVAG, that's 2.5, based on example result on WM data from the last slide. Part of the task of estimating the cumulative traffic in the design lane over the design period is to estimate the likely changes in daily traffic loading during this period. The compound growth of traffic volumes is usually and conveniently specified as a percentage increase in annual traffic volumes. A typical statement being the annual growth rate is R%. So adopting this specification of growth and with compound growth occurring throughout the design period, the cumulative growth factor, the CGF, over the design period to be calculated as this formula, as shown here. Where the R is the annual growth rate in percentage, and the P is the design period in years. So refer to previous slide, the R equals to 4 and P equal to 20. So CGF could be calculated as 29.8. So because the R that's greater than 0, so we use the top formula. On the other hand, we can also find the value of CGF from the table 7.4 as shown below, where the second horizontal row is the annual growth rate. And first vertical column is the design period in years. We could also find the value of 29.8 from this table. The horizontal row, that's 4, and vertical, that's 20. So we can find this value. So there are two ways of getting the CGF. When iterating all the values to equation 14, the NDT could be calculated as 2.9 times 10 to the power of 6 HVAGs. So we can see that in this case, the NDT is the design traffic is priced in HVAGs. The NDT for flexible pavement often is priced in terms of SAR or ESA. So we will convert HVAGs to SAR or ESA, and we will go to more details in the next few slides. For flexible pavements, we need to calculate the allowable ESA per actual group and SAR per ESA. Afterwards, we need to calculate the design ESA and design SAR for each distress type. And then we can make a comparison of this allowable and design values. If we want to convert the design traffic loading units in HVAG and SAR, and vice versa, we need to use the damage indices, ESA over HVAG, SAR over HVAG, and SAR over ESA. This is the triangle relationship between NDT in HVAG, NDT in ESA, and NDT in SAR. Then you may ask, why using different units? This is because the allowable traffic is normally expressed in terms of ESA or SAR. So we need to use these relationships to make the conversion. The pavement design by mechanistic method, how to consider appropriate types of damage. In design of granular pavements with thin bituminous surfacing, only one type of damage is considered, namely the overall deterioration of the pavement, reflecting the increased level of roughness and rotting. So however, for pavements containing one or more bond layers, up to 3 distinct types of damage are considered. The fatigue damage to asphalt, SAR5, the rotting and loss of surface shape, SAR7, and fatigue damage to cemented material, SAR12. They are the allowable traffic calculated using the damage models in SAR units. The damage and distress models for different material types are shown below. So we have seen these formulas in lecture 7. The allowable traffic from these damage models are expressed in units of SAR5, SAR7, or SAR12, corresponding to this component of damage model M. So if we equal those doubles, then mu epsilon doubles. Correspondingly, from these damage models, the N decrease by the ratio of 2 to the power of M, and damage increases by ratio 2 to the power of M. You may think, if all actual groups in traffic are identical and impose the standard actual load, then there's no need for different units. But real situation is far more complex, as traffic has a different combination of actual group loadings. Say traffic has 3 actual group loadings. First group carries 0.5 standard load. Second group carries 1 standard load, and third group 2 standard load. It is obvious the same traffic imposes different damage in terms of total SL to different materials based on the damage models. So from this table, we are able to work out the total damage to different materials from these 3 different actual groups. The pavement structural design carries the allowable traffic loading reputations are greater than or equal to the design traffic loading reputations. So comparison needs to be based on the consistent units, the ESA or SAR5 or SAR7 or SAR12 for all possible damage or distress failure modes. If the units are not consistent, then we need to convert the units of the design traffic loading. So here we introduce the concept of standard actual. The equivalent standard actual ESA was developed as an index of loading to express permanent damage caused by all these actual group loads of various actual. So ESA isn't a physical identity itself, it's an index of loading that enables you to look at the combined damage of different actual group loads and tears. And it expresses that damage in terms of equivalent passes was standard actual. So in the flexible pavement design process, the first step in assessing the ability of a pavement configuration to withstand the design traffic is to determine the extent of damage caused to the configuration by a reference actual group termed the standard actual. As shown on the slide, here is the definition of standard actual. The standard actual is a single actual with two tiers. And a load of 80 kilonewton on the actual. The standard actual is the reference damage load. So loads on different actual configuration with dual tiers that cause the same amount of damage as the standard actual are contained in this the right table. So for example, 181 kilonewton on a triaxial with dual tiers causes the same rotting damage as 80 kilonewton on our single standard actual. So designs are based on equivalent number of standard actuals. Damages of all other actual loadings are referenced to it as the number of equivalent standard actual repetitions. Previous table is for standard actual from dual tiers. Loads on actual groups with single tier, which cause the same damage as the standard actual is shown in this table. And the load varies with the actual group type and nominal tier section width. Actual load from these actual groups is the equivalent of one standard actual repetitions, SAR. To calculate the SAR of damage, a procedure is required to calculate the damage associated with each actual group of each actual type in the traffic load distribution relative to the damage caused by a standard actual. The loads on actual configurations that causes the same amount of damage as the standard actual could be referred from the above two tables. For each actual group carrying a certain load Lij, it could be converted into an equivalent number of standard actual repetitions or specific type of damage characterized by damage exponent M as the following equation. So in this equation, SAR Mij is the number of standard actual repetitions, which causes same amount of damage as a single passage of actual group I with load Lij, where a load damage exponent is M. As I is the standard load for actual group I, we can refer to the values in previous two tables. The Lij is the J's load magnitude for actual group type I, and M is the load damage exponent for different damage type. The M exponent in the above equation is taken from table 7.7. So for empirical design of granular pavement with seam bituminous surfacing and for overall pavement damage, M equal to 4, and the damage unit is ESA. Within the mechanistic design of pavement with one or more bond layers, the fatigue damage of asphalt has a damage exponent of 5 and damage unit of SAR5. While rotting and loss of surface shape has damage exponent of 7 and damage unit of SAR7. The fatigue damage of cemented materials has damage exponent of 12 and damage unit of SAR12. So during design, we need to calculate the total ESA or SAR for each relevant damage type using the parameter M in this table. From equation 16, we can see that damage increases exponentially with load. For example, the actual load carrying twice the load of standard actual causes the same damage as 2 to the power of M standard actual repetitions, as shown here. Now let's look at one example to determine the damage indices using equation 16 for a road pavement based on the collected data shown in traffic load distribution table H1. The damage indices, in other words, ESA over HVAG, SAR over HVAG, and SAR over ESA, project based and vary for specific road and traffic load distribution. The left is the project traffic load distribution table. So the first column is the magnitude of actual group load. The other columns are the percentage of each actual group type for different actual group load. The total proportion of each actual group is 1. The red table is the project traffic load distribution by proportion of actual groups of each type and load. For example, the project traffic load for actual group of 10 kilonewton and actual group type of SAST is calculated as 0.2569 divided by 100 times 0.3799, and we get a value of 0.000976. Then we are able to calculate the SAR for damage exponent of 4, 5, 7, and 12 according to equation 16. For granular pavement with thin surfacing, M equal to 4. For asphalt fatigue damage, M equal to 5. So for the first value in the bottom line of the left table, the SAR is calculated as 400 divided by 53. Because it is single actual with single tear SAST, and nominal tear section width is less than 375 millimeter. So the standard actual load is 53 kilonewton here. And when it plugged into this formula, we get a value of 3,244.4. Similarly, the SAR for rotting, a loss of surface shape, is M equal to 7, while SAR for fatigue of cemented materials is M equal to 12. We're able to calculate the corresponding SAR as well, and they are summarized in those tables. The table H4 is SAR multiplied by the proportion of each actual group load of each actual group type in the project traffic load distribution. In other words, table H4 equals to table H2 times table H3 with damage exponent of 4, 5, 7, and 12. For example, for actual group load of 140 kilonewton and actual group type of SASD and damage exponent of 4, the value is 2.01 times 10 to the power of -5 times 48.687. So both values are taken from the previous two tables, table H2 and table H3, and finally we get a value of 0.00098. The sum of the entries in this table is 0.8, and that's ESA over HVAG. Similarly, the average SAR5 over HVAG for M equals to 5 is the sum of the calculated values in the right table, and it is 0.96. So similarly, for the damage exponent of 7 and 12, the damage index SAR7 over HVAG and SAR12 over HVAG are calculated and shown in these tables. From previous table H1 to H4, the damage index values are summarized in table H5 below. The indices represent the damage in terms of ESA or SAR per HVAG of project traffic for each damage type. Based on these indices, we are able to convert the traffic loading from one unit to another. Now let's look at one example to see how to calculate the design traffic in terms of ESAs and SARs and how the conversion is done. We could use traffic data from example 3 and the project-specific WIM data from example 4 and tables H1 to H5 to estimate the standard actual repetitions per ESA and determine the design ESA and SAR for the relevant damages. If we divide SAR over HVAG by ESA over HVAG, then we get the SAR over ESA values as shown in table H6. So if we know the values of the damage index, we could convert the traffic units from ESA to SAR or the other way around. The design traffic loading is normally expressed in ESAs or SARs. So if we know the design traffic loading NDT in HVAG and the damage index for flexible pavement, then the design traffic loading NDT in ESA could be calculated as DSA equals to NDT times ESA over HVAG equals to 2.9 times 10 to the power of 6 times 0.8. And we get a value of 2.3 times 10 to the power of 6 ESA. So the ESA is NDT in ESA units. Similarly, the SAR5 is NDT in SAR5 units. The SAR7 is NDT in SAR7 units. And the SAR12 is NDT in SAR12 units. Apart from DSA, if we want to calculate the SAR5, the SAR7, and the SAR12 for flexible pavement, we're able to multiply the DSA by the corresponding SAR or ESA values from table H6. The resulting values are given in table H7. Another way of calculating the SAR is to multiply the NDT by average SAR per HVAG in table H5. For example, the SAR7 equals to 2.9 times 10 to the power of 6 times 1.67, and we get which is the same value as the one in the table above. Now it's time to look at the flexible pavement mechanistic design procedure. Table 8.1, 8.2, and 8.3 list in detail the steps which are required to carry out the mechanistic design procedure. The procedure consists of evaluating the input parameters, then select a trial design and determine the allowable traffic. Finally, compare it with the design traffic and decide to accept or reject the trial pavement. In general, there are 18 steps to follow. Most steps were already covered in previous slides, so I just briefly go through them. You may need to use all of them or some of the steps. The first one is to select a trial pavement and desired project reliability. Then calculate the elastic parameters for the subgrade materials, the E, the mu, and G, followed by the elastic parameters for the top sublayer of the granular layer, and then elastic parameters and thickness of the other granular sublayers. If relevant, we need to determine the elastic parameters for cemented materials and their pre- and post-fatigue cracking. Next, we need to determine the elastic parameters for asphalt, then adopt the subgrade strength criterion for damage type of rotting and shape loss. So afterwards, we need to determine the fatigue criteria, both for cemented materials and asphalt. The 10th step is to calculate the design standard axial repetitions SAR for each relevant distress mode. For the analysis, we assume approximate standard axial view loading, then determine the critical locations in the pavement for the calculations of strength. Step 13 is to input the given conditions to circulate to determine the maximum vertical compressive strength of the subgrade and maximum tensile strength at the bottom of the cemented and asphalt layer. Sometimes we need to calculate the critical strength for both pre-cracking and post-cracking. So if the post-failure cracking phase of cemented materials is considered. For the interpretation of the results, we need to calculate the allowable number of standard axial repetitions for each of the relevant distress mode. For step 15, we compare the allowable number of standard axial repetitions with the design number of standard axial for each distress mode. The pavement is deemed acceptable if all distress modes, the allowable number of standard axial repetitions exceeds the design number of standard axial repetitions. Otherwise, it is deemed unacceptable, then we need to select a new trial pavement and repeat steps 1 to 16. So finally, sometimes we also need to compare the alternative acceptable designs. I will show you one example with 3 types of flexible pavement to help you to understand the above design procedures. This example is the mechanistic design of flexible pavement using the following design parameters. Subgrade design CBR of 5%. Design traffic for 30-year design life is 10 to the power of 7 HVAG. Traffic load distribution is shown in the right table. Operating temperature or effective temperature is WMAPG equal to 28 degrees. Design traffic speed is 60 km per hour. Asphalt modulus for size 14 millimeter and 20 millimeter mix. The desired project reliability is given as 97.5%. Let's design the following 3 flexible pavement types. The spread seal surface or thin bituminous and bond granular pavement. The asphalt pavement containing a cemented material subbase and full depth asphalt pavement. These are typical flexible pavement types, so let's discuss one after another. Let's look at case 1. The spread seal surface unbound granular pavement. Such pavement is composed of a spread seal layer, an unbound granular layer, and a subgrade. Spread sealing is achieved by spraying a thin film of bituminous binder onto a road surface and then covering it with a layer of aggregate. For the trial design, the first step is try pavement composition with thin top spread seal surface and for 475 millimeter unbound granular material and subgrade design CBR of 1%. The step 2 is to calculate subgrade properties. When CBR equal to 5%, EV equals to 50 megapascal. As EH equals to half EV, for unbound materials. So EH equals to 25 megapascal, mu V equals to mu H equals to 0.45. So shear modulus G could be calculated as EV divided by 1 plus mu V, and we get value of 34.5 megapascal. Step 3, for granular materials placed directly on the subgrade, sublayering is required. The calculation is similar as the example in the last lecture. So EV1 is the minimum of the value from the formula and from the empirical table, which is 500 megapascal. And EH1 again is half EV1, so it is 250 megapascal. The mu V1 equals to mu H1 equals to 0.35 are taken from table 6.3. So shear modulus G1 is calculated as 370.4 megapascal. The ratio R is calculated as EV1 divided by EV subgrade to the power of 0.2, and we get the value of 1.585. Step 4 is the calculation of the elastic parameters for the other granular sublayers. We divide the total granular thickness into 5 equal thick sublayers with 95 millimeter thick for each layer. The elastic parameters for the second granular sublayer from top are EV2 equal to EV1 divided by R equals to 315 megapascal. Correspondingly, EH2 is 157.5 megapascal. So since mu V2 equals to mu H2 equal to 0.35, we could get the shear modulus as 233.3 megapascal. We're able to follow the same procedure to calculate the other sublayers 3, 4, 5. A summary of the calculated material properties are given in the following table. The step 5 and 6 are for cemented materials and asphalt. We don't need to calculate them as they are not relevant to this case. Step 7 is to use the subgrade strain criterion to calculate the permanent deformation allowable loading using this formula, as shown here. And step 8 and 9 are again for cemented material and asphalt, and they are not relevant here as well. Step 10 is to determine the design number of standard actual repetitions (SAR) for each relevant distress mode. Since NDT, that's 10 to the power of 7 and HVAG, and for this case, the permanent deformation in subgrade is the controlling distress mode. Firstly, we need to calculate the ESA as NDT times ESA over HVAG, and we get the final result of 0.7 times 10 to the power of 7 ESAs. This DESA could be used in the empirical chart in figure 8.4 to determine the thickness of the granular materials, which I will just show you later on. Since SAR7 over ESA equal to 1.6, so that's the given condition of all three cases. So DSAR7 could be calculated as DESA times SAR7 over ESA. So this is 1.6, that's SAR7 over ESA times DESA. And we are able to get the result of DSAR7. So that's 1.1 times 10 to the power of 7 SAR7s. The SAR7 is normally used if designing by mechanistic method. Step 11 is to assume approximate standard actual view loading. The standard actual load is represented as TR Pavement contact stress as 750 kilopascal, the load radius of 92.1 millimeter, and 4 circular contact areas. Step 12 is to determine the critical locations to calculate strengths, which are top of subgrade, directly beneath one of the loaded views, and midway between the loaded views. In previous lecture, we know the locations of critical strengths are the tensile strength at the bottom of the asphalt, the tensile strength at bottom of cemented materials, and compressive strength at the top of subgrade. Since this case contains a spread seal instead of asphalt layer on top, we do not need to consider tensile strength at the bottom of asphalt. It did not contain the cement layer, so we do not consider the tensile strength at the bottom of the cemented materials. So we only consider the compressive strength at the top of subgrade. And one is directly beneath one of the loaded views, and another one is midway between the loaded views. So one is here, and the other one is here. So we only consider the compressive strength. So once you input the given parameters in the circuit, you are able to get the corresponding compressive strength. From the circuit analysis result, it is found that the maximum vertical compressive strength is 906 μ-epsilon, which is midway between the two loaded views. Step 14 is to calculate permanent deformation allowable loading from step 7 in combination with the above maximum compressive strength. The result is 1.2 times 10 to the power of 7 SAR7. Step 15 is to compare the allowable loading with the design traffic. The allowable loading is greater than the design traffic. So we draw the conclusion in step 16 that the trial composition is acceptable. This design was done using mechanistic procedure. For granular pavement within bituminous surfacing, we could use empirical design chart in figure 8.4 to select the thickness of granular materials for trial design. So for flexible pavement with unbound granular material layers, which are surfaced with either a bituminous seal or asphalt layers up to 40 millimeter thick, we could follow the mechanistic design procedure. As it has not adequately accounted the effect of traffic loading on the seam surfacing, we could also use the empirical design chart given in figure 8.4 to determine the thickness of unbound granular materials required over the subgrade. For this empirical design chart, the design traffic loading in the horizontal axis is in ES8. So you calculate the number of load repetitions in equivalent standard actuals over the design period. The other factor is the thickness, depends on is the CBR or Californian bearing ratio of the materials that is going to be covered by the pavement. So it's shown on the right-hand side axis. Each of these curves here relates to different Californian bearing ratio, so different strengths of the supporting layers. For this example here, the subgrade has a design CBR of 5, and we had a design traffic loading DSA of 0.7 times 10 to the power of 7. So we are able to find the corresponding thickness of granular materials overlap the subgrade. As 475 millimeter. So that gives the cover requirements over the subgrade to inhibit it deforming and resulting in surface deformation to an acceptable level. So that controls the amount of deformation in the subgrade by providing that amount of cover. The other way is to iterate the DSA and CBR into this formula, and we could work out the same value. This design chart is applicable to pavement with design traffic loading of 10 to the power of 5 to 10 to the power of 8 ESAs. Now let's look at case 2. Asphalt pavement containing cemented material subbase. Again, we select 12 pavement composition in step 1. Size 14 millimeter asphalt, E equal to 2,200 megapascal, and thickness of 50 millimeter. Below it is size 20 millimeter asphalt, E equals to 2,500 megapascal, and thickness of 125 millimeter. The cemented materials has E equals to 2,000 megapascal with thickness of 150 millimeter. Below it is the granular material layer with thickness of 200 millimeter. The subgrade is semi-infinite with CBR of 5%. The project reliability is set as 79.5%. This is a trial design, and we need to check if it is acceptable. If a pavement contains a cemented layer which reaches its allowable loading in terms of fatigue, the pavement may then enter a post-cracking phase. Depending on the pavement configuration, there's useful life after the cemented material has fatigue cracked. And so in our mechanistic calculations, we allow for that post-cracking life of the materials. So this might be a situation where you have 200 millimeter asphalt overlying a cemented treated material, and that's used as a subbase. If that cement material cracks, there's still some useful life left in that pavement as far as the road user is concerned. It still performs okay. That cracking wouldn't come through to the surface, and there's some useful life left after that. So here, normally the asphalt layer on a cemented material subbase pavement is equal or greater than 175 millimeter. Then they would be modeled by considering the fatigue lives of both the cemented layer and the asphalt layer pre and post cracking. So we need to calculate the fatigue and permanent deformation from the critical strength for both the pre-cracking and post-cracking cemented material phase. Otherwise, we do not need to consider post-cracking if asphalt thickness is less than 175 millimeter. Step 2 is to calculate the elastic properties for subgrade with CBR of 5%. This is similar as in case 1. We could get the values of EV, EH, μV, μH, and G. For step 3, again, the modulus of top granular sublayer is the minimum of the value from design formula and empirical table. So therefore, the top granular sublayer, the EV1 is 152 megapascal. All the other elastic properties could be worked out accordingly, because we already practiced multiple times. So I won't just go into more details here. Step 4 is the elastic property calculation for the other granular sublayers. Firstly, we need to get the R value. Since this is granular materials placed directly on the subgrade, sublayering is required. We divide the total granular thickness into 5 equal thick sublayers. Each has a thickness of 40 millimeter. Then we are able to calculate the elastic parameters, the modulus, the Poisson's ratio, and shear modulus of the second granular sublayer. We could repeat the procedure for the other sublayers. The below table is a summary of the elastic properties of the unbound granular sublayer and subgrade from step 2 to 4. Step 5 is to determine the elastic parameter for cemented materials. As discussed, we need to consider both the pre-cracking and post-cracking cemented material phase. For pre-cracking material phase, we could choose E and mu from table 6.7. For the purpose of mechanistic modeling in the post-fatigue phase, cemented materials may be assumed to have a presumptive vertical modulus of 500 megapascal and a Poisson's ratio of 0.35. We could work out EH and G accordingly. Please be aware that there's no sublayering for post-cracking cemented materials. For asphalt, we set the Poisson's ratio as 0.4. According to the modulus and the Poisson's ratio, we are able to calculate the shear modulus. The elastic properties of all materials, the asphalt, the cemented material, the granular material, and subgrade are summarized in the below table. The subgrade strength criterion, the cemented material fatigue relationship, and the asphalt fatigue relationship are used to calculate the allowable standard actual repetitions for each distress mode. Step 7 is to adopt the subgrade strength criterion. Step 8 is to determine fatigue criteria for cemented materials using this formula. We are referring to table 6.8, reliability factor RF equal to 0.5 for 97.5 project reliability. Step 9 is to determine fatigue criteria for asphalt using this formula. Where the RF is taken as 0.67 from table 6.15 for 97.5 project reliability. The effective volume of bitumen VB is taken as 11%. Step 10 is to determine the design number of standard actual repetitions SAR for each relevant distress mode. For the given condition of NDT and ESA over HVAG equal to 0.7, we could work out the DESA as 7 times 10 to the power of 6 ESAs. The following damage indices allow us to convert the traffic loading from SAR to ESA or ESA to SAR. Same as case 1, step 11 is to assume approximate standard actual view loading. Step 12 is to determine 3 critical locations to calculate strength from software circuitry, both for directly beneath one of the loaded views and midway between the loaded views. The critical strengths from circuitry outputs are the maximum strengths for pre-cracking cemented material phase, as shown in the top table, and post-cracking cemented material phase, as shown in the below table. We are able to use these strength values for the calculation of traffic loading. Step 14 is the calculation of allowable traffic loading. Because the thickness of asphalt over cemented material is 175 millimeter, we need to calculate for both pre-cracking and post-cracking phase. To calculate the total allowable loading of the pre-cracking and post-cracking fatigue phases, the allowable loading needs to be expressed in terms of equivalent standard actuals, ESA, rather than standard actual repetitions, SAR. For pre-cracking phase and cemented materials fatigue, the N could be calculated using this formula as shown here. And we can convert the unit from SAR 12 to ESA through dividing the value by 12. For permanent deformation of sample grade, the N could be calculated using this formula and then convert it to ESA through dividing the result by 1.6. For pre-cracking phase and for asphalt fatigue, we use this formula to calculate N, and it is divided by 1.1 to convert to ESA. So normally for the design of pre and post-cracking cemented materials, traffic loading is converted to a common unit, the ESA, for all distress or damage types. So we are able to maintain the consistency of the unit for calculation of the total allowable loading. Previous slides are the calculation of the allowable traffic loading for the pre-cracking phase. Now we need to calculate allowable traffic loading for the post-cracking phase. The formulas for subgrade permanent deformation and asphalt fatigue are the same as before, and we only need to replace the pre-cracking maximum strength by post-cracking maximum strength. The units of the calculated allowable loadings are then converted to ESA. So post-cracking phase of cemented material, we do the calculation, and the unit as AR7, we have to convert to ESA. And similarly, as for the asphalt fatigue, we have to use the post-cracking strength to do the calculation and convert the unit from SAR5 to ESA. The equations to consider the post-cracking of the cemented materials are equation 23 and 24. The equation 23 is asphalt fatigue, and the expression is shown here. The NA is the total allowable loading to asphalt fatigue in ESA, and NC is the allowable loading to cemented material fatigue or pre-cracking. N1 SDA is allowable loading to asphalt fatigue prior to cemented material fatigue or pre-cracking. And second A is the allowable loading to asphalt fatigue after cemented material fatigue or post-cracking. It is only applicable when NC is less than first A, otherwise we may get negative value. The equation for permanent deformation is shown in the below formula. The NS is the total allowable loading to permanent deformation in ESA. And first S is the allowable loading to permanent deformation for cemented material during pre-cracking. And second S is allowable loading to permanent deformation after cemented material fatigue or during post-cracking phase. Also, this equation only applies when NS is less than N first S. Therefore, the total allowable loading of pre and post-cracking phases are as follows. The asphalt fatigue allowable loading could be calculated using the equation 23, and all the values are obtained from the previous steps. So we get the final value of 7 times 10 to the power of 6 ESA. Well, permanent deformation allowable loading of subgrade could be calculated using the equation 24, and we obtain the final value of 1.2 times 10 to the power of 7 ESA. Same as the last slide, you can see the labels for the meaning of each number in these two equations. Now we need to compare the total allowable traffic loading to design traffic loading in ESAs. For subgrade permanent deformation, n equal to 1.2 times 10 to the power of 9 ESA, and for asphalt fatigue, n equals 7 times 10 to the power of 6 ESA from previous slide. Previously, we also calculated the design traffic as NDT equal to 7 times 10 to the power of 6 ESA. As the allowable loading for each distress mode is equal or greater than design traffic, we could draw the conclusion that this trial pavement composition is acceptable. For this case, the asphalt thickness is 175 millimeter. So we calculated the values for pre-cracking and post-cracking stage. In another case, if the asphalt thickness is less than 175 millimeter, then we only need to consider the pre-cracking phase, make the comparison, and draw the conclusion. Now let's see case 3, the full depth asphalt pavement. There are thick asphalt layers directly above the subgrade. Again, step 1 is to try pavement composition. We have size 14 asphalt and size 20 asphalt and subgrade with CBR of 5%. And it is semi-infinite. Step 2 is for elastic property of subgrade. As we have done this a few times, I won't go into more details here. There are no granular and cemented materials, so we could omit step 3 to step 5. Step 6 is the same as that in case 2. We have the E and mu for both size 14 millimeter and 20 millimeter asphalt. Step 7 is to adopt the subgrade strength criterion. Step 8 is not relevant as it is for cemented material. Step 9 is to determine fatigue criteria for asphalt using this formula. Where the RF is taken as 0.67 from table 6.15 for 97.5% project reliability. And again, the effective volume of bitumen, the VB, is taken as 11%. Step 10 is to determine the design number of standard actual repetitions, SAR, for each relevant distress mode. From the given condition of NDT SAR5 over ESA, SAR7 over ESA, and ESA over HVAG, we could work out DSA, DSAR5, and DSAR7. In previous case, we convert the unit to ESA because we need to plug in all values in total allowable loading formulas. But for this case, we don't need to calculate post-cracking as there's no cemented material. So we use damage units of SAR5 and SAR7 for comparison. Step 11 is to assume approximate standard actual view loading. Step 12 is to determine two critical locations the top of subgrade and bottom of asphalt to calculate strength from software circuitry, both for directly beneath one of the loaded views and midway between the loaded views. From circuitry software, we are able to obtain the maximum strength for asphalt and subgrade in step 13, and the results are shown in the below table. For the asphalt, the maximum strength occurred between two views, and for the subgrade, the maximum strength occurred beneath the views. Step 14 is to calculate allowable traffic loading, both for asphalt fatigue and subgrade permanent deformation. Next step is to compare the allowable traffic loading to the design traffic loading in terms of SAR5 and SAR7. Step 16 is the conclusion. We concluded that since the allowable loading for each distress mode is greater than the design traffic, this trial pavement composition is acceptable. I hope through these three cases, you are able to master the design procedure of flexible pavement. For the circuitry software, it uses the cumulative damage factor, the CDF, which is the ratio of design traffic and allowable traffic loading. They have to maintain the same units to work out CDF. If the CDF is less than 1, then the road is safe with excess capacity, and the CDF represents the ratio of life spent. If the CDF equals to 1, it means the road has just reached its life. Otherwise, if the CDF is greater than 1, then the road has exceeded its life and been damaged. Obviously, additional loading will cause further damage to the flexible pavement. Now it is the summary of this lecture. We have learned the method to calculate the design traffic NDT in terms of HVAGs using equation 14. Then the mechanistic procedure to estimate the average number of axles per vehicle group and HVAG from WIM, weight in motion data, based on the sum of the proportion of steer axles, SASD and TASD. Next are the concepts of different units of traffic loadings, HVAG, ESA, SAR5, SAR7, SAR12, based on damage or distress models. We also learned the mechanistic procedure to estimate damage indices, for example, ESA over HVAG, SAR over HVAG, SAR over ESA. Finally, we go through 3 typical flexible pavement design cases. The mechanistic and empirical procedures to design a flexible pavement with thin bituminous surfacing, normally less than 40 millimeter, and mechanistic procedures to design asphalt pavement containing cemented layer. In this case, we have calculated the total allowable loading from both pre and post cracking traffic loadings. Finally, the mechanistic procedures to design the full depth asphalt pavement. Okay, well, that's the end of our lecture today. Thanks for listening and have a wonderful day.